also crystal field stabilization energy and the splitting of the orbitals. Why is it different for tetrahedral compared to octahedral? All that stuff we have given you details of how these things work out and why the complexes are colored, why they have different magnetic moments when you change the ligands. So all that stuff. Any questions so far on that? I think we also uploaded the video, right, on the last week's lecture on the website. So we'll also do the same thing for today's lecture too, for those of you who could not attend the lecture. So let's review our Jahn-Teller distortion. We basically said, if you have a situation such as for the copper 2 plus, where you have a D9 configuration, can you all see this? In the D9 configuration, you have the splitting of the d orbitals in an octahedral field, giving you Eg and T2g orbitals. Eg is the x squared minus y squared and the z squared orbitals, and here xy, yz, and zx. These are the T2g orbitals. So when you fill in the number of electrons here, you get a situation like this. You can have a pair of electrons in x squared minus y squared, or you may have a pair of electrons in the dz squared, because these two have the same energy. What the Jahn-Teller distortion theorem tells us is that if your electronic ground state electronic configuration is degenerate, then you don't have a choice to place the electrons here or there. The nature will decide it so that it will split the orbitals into two, one with a lower energy, one with a higher energy. So, for example, the lower energy could be x squared minus y squared, or it could be z squared also, dz squared orbital. Unless you do an experiment, you will not be able to know which one is stabilized. All right. Similarly, the upper orbital could be dz squared or x squared minus y squared. Now, the implication of placing those pair of electrons in x squared minus y squared tells you that if you look at the octahedral geometry, the x squared minus y squared is directly head-on with the ligands. So when you have a pair of electrons here in the dx squared minus y squared, these electrons will repel the electrons of the ligand in a way that you have a basal expansion of the octahedra. So the octahedra will be expanded along the x and y axis. That expansion is caused by the repulsion of electrons in the x squared minus y squared and the ligand electrons. On the other hand, if you were to have pair of electrons in the dz squared level, then the axial ligands that are on the top and the bottom, they get elongated. Again, Jahn-Teller theorem does not tell you which ones get elongated, which ones get contracted. What it tells you is you cannot have a perfect octahedra. So that's what I think we were discussing as time was running out last time. So this is a good time to take any questions from the class. Otherwise, we'll continue with some examples to see which complexes show Jahn-Teller, which will not show. So in the exam, if I give you a bunch of complexes and ask you to predict which ones will show Jahn-Teller distortion, which ones will not, you should be able to work out the same mechanism, the way we are doing it, and be able to answer. Any questions? Anything that's not clear up to this point? If not, we will take some examples and see. The question here is, let's say if I have two complexes, titanium aqua 3 plus complex and manganese H2O6 4 plus complex. So if you're asked to predict which one will be near perfect octahedra, then we need to look at their electronic configurations to see if they qualify for a Jahn-Teller distortion. So let's do this. With the titanium 3 plus, the electronic configuration of titanium 3 plus is argon 3d1. Titanium 3 plus has one unpaired electron in the d level. So in the octahedral field, you will have just one electron in the T2G and none in the EZ. right? So let's go with the manganese here. I have manganese 4 plus. Manganese 4 plus is argon 3d3. So if you now look at the octahedral crystal field splitting on this, you have 3 electrons in here. Right now, if you compare the electronic configurations of titanium 3 plus and manganese 4 plus, one thing is very striking. In the case of T2G, in the case of titanium 3 plus, you can have the electron here XY, YZ, or ZX. That's the choice you're seeing here. So in other words, you have 3 choices here. You can place this electron here, there, or there. That's exactly what the Antonov theorem tells us. You cannot have a choice in a nonlinear molecule, such as an octahedra. So what happens is, this stuff must distort to lower one of the energies where that electron will preferentially go. So definitely you will see Antonov distortion in the titanium 3 plus complex. Now let's argue for the same thing for the manganese 4 plus. In the case of manganese 4 plus, I have 3 electrons and 3 states. So you don't have too much of a choice here, or you're going to get anything different by placing the electrons in different orbitals. So in this case, the Jahn-Teller theorem would not apply. So this will not show any distortion. Is it making sense? So the distortion comes only when you have a degenerate set of orbitals and you have a choice of placing the electrons either in the empty, or the filled levels.
So it would be distorted even if you had 2 electrons in the TG2?
Yes.
Okay.
In fact, if I were to change this example from manganese 4 plus to, let's say, manganese 3 plus, okay? Suddenly I have 3D4 configuration, correct? So in a 3D4 configuration, I have in a high speed strong field ligand, I will have that electron there. Now I have a choice here. I can put the pair of electrons in XY, YZ, or ZX. Suddenly, manganese 3 plus qualifies for a Jahn-Teller distortion. So any compound that has manganese 3 plus generally comes with a distortion. So you will never get pretty looking octahedra. In fact, in a solid state chemistry, these distortions can be cooperative, not at the molecular level, but at the crystal level. And you can have what you call a cooperative Jahn-Teller distorted structures. And they show very interesting properties. Questions up to this point, folks? Okay. Gurveer, is that clear for you?
Yes, thank you.
Okay, good. All right, so the next thing that we're going to talk about is what we call the activity of complexes. So, as you all know, in chemistry, some chemicals are active, some are inert. The same thing happens with the coordination complexes too. Some are extremely active, some are inactive. Inactive for what? For example, if I have a complex with ligand L, and if you were to treat that complex with a new ligand, the question is, do I get this quickly? So when I use the word quickly, some of you may be wondering what exactly is quickness. So here is the definition. If I have a complex of 0.1 molar concentration, and if all its ligands can be exchanged with the new incoming ligands in less than a minute. So if this replacement is finished or completed in less than a minute, then you say the complex is active, or we use the word labile. Labile means active. On the other hand, if this complex takes more than 1 minute, to exchange all its ligands, then we call this inert. So T greater than 1 minute is inert, T less than 1 minute is labile. Please keep in mind that these words labile and inert have nothing to do with the thermodynamics. Let me give you an example of how these things operate. So let's look at a real life complex, not L and L plus. Let's see that if I have hexamine, cobalt, hexamine, cobalt 3 complex, and if I were to treat this with H2O and in the presence of acid, so the expected complex is going to be 3 plus 6 NH4 plus ions. This is what you would expect by replacing the original ligands of this complex, which are amine ligands, with water. And that replacement should lead to this. Now, if I look at the equilibrium constant for this process, it's more than 10 to the 25. So what does that tell you about the activity of the complex? Is it spontaneous or not non-spontaneous process? When you see such a high equilibrium constant, what does your pChem tell you?
I think it's spontaneous, very
It
spontaneous.
must be spontaneous. You are absolutely correct. Because when your K value is greater than 1, then it has to be spontaneous. If it is less than 1, then it is non-spontaneous. Okay, guess what now? If you were to do this reaction in the lab, although the reaction is spontaneous, it will not happen instantaneously. Watch my words, spontaneous and instantaneous. Spontaneous means it is bound to happen, but there is no time frame for that to happen. On the other hand, instantaneous means it has to happen quickly. In this example, what we find is, although the thermodynamics tells us that the reaction should go to the right, the kinetics is so sluggish that this reaction, you can wait for thousands of years, nothing will happen. This is a familiar story. I'm sure all of you know. If you look at carbon, right? Carbon has 2 forms, carbon in the diamond form and carbon in the graphite form. Anyone knows which one is thermodynamically more stable? Any thoughts on this? Only 2 choices. Is it graphite or what is the standard state of carbon? That tells you which one is more stable. So clearly, I don't know, I'm not hearing anybody. Maybe your mics are muted. Tony Lopez, can you tell me which one is more stable? Any idea? Tapia, do you have any idea about whether it is, which one is stable?
I would say the graphite.
You're absolutely correct. It is the graphite that is stable. So diamond being unstable, at some point, all the diamonds that we have must convert to graphite. But does it happen instantaneously? So to put it another way, from a thermodynamic sense, diamonds are not forever because some of the diamonds will get converted to graphite. But in the kinetic sense, that is not how it happens. You have never seen your diamond converting into a piece of graphite, which is absolutely no value. So they are kinetically sluggish. So that's exactly what happens in the coordination complexes too. Even though this complex is supposed to be spontaneous, but it takes so many years that we say this complex is inert. So hexamine cobalt 3+ complex is inert by the standards. Now, some of you may argue, well, I have amine and I have a water. Now the chemistry is so different. So how do people know that the ligands are not playing a role in terms of its lability or inertness? So what generally scientists do is to find out if something is labile or inert, they do what they call radioactive labeling. So for example, if I have tetracyanonickelate 2-, that's a complex. Now what you do is you try to replace that with a cyanide that is labeled. So in other words, you use carbon 14 cyanide and then carry out the reaction to see how much of radioactivity is in this complex that you see and how long it takes. So what you do is you carry out the process. After 1 minute, you take that complex out and then look at how much radioactivity it has. So if your radioactivity is consistent with the complete replacement of cyanides, then you can say the complex is labile. If not, it should be considered as inert. Am I making sense? So if you want to avoid any effects because of the chemical composition of the ligands, then this is how you do what you call radioactive labeling. So it eliminates all the possibilities. It basically tells you whether this complex is active in the sense how quickly it can exchange its ligands, as opposed to inert, which means this metal is holding on to the ligands very tight. So it does not allow those original ligands to be replaced by the incoming ligands. Am I making sense, folks? So people have worked on thousands of complexes. They came up with a set of rules that kind of tell us which complexes are generally labile and which are generally inert. Okay, so I'll give you some rules that we can follow to predict the kinetic activity of these complexes. But before I do that, are there any questions on this? So I kind of summarized the differences between spontaneity and instantaneity and kinetics and the thermodynamics. So in looking at the activity of complexes, thermodynamics is of little help because the reality is dictated by several other conditions, not driven by the thermodynamics alone. So let's write down the rules for predicting the lability or the inertness of complexes. So rule number 1, smaller metal ions hold on to their ligands. What do you expect? They hold on to the ligand strongly or weakly?
Would it be strongly?
Stronger, absolutely correct. The strong and hence or inert. Am I making sense here, folks? So if you have, let's say, a titanium H2O6 3+ and a manganese H2O6 3+. which one is expected to be inert? It's titanium complex or the manganese complex? To understand that, we need to know what the sizes of these ions are. We have titanium 3+ and then manganese 3+. So what happens is the size of the atoms as you go from left to right in the periodic table? Does it increase or decrease?
Increases.
Hmm?
Increases.
Is that true?
Well,
I thought it decreased.
they're in the same shell both, so
Yeah,
it
they're the
doesn't decrease,
same,
yeah.
same period, yes. As you go from left to right, the size of an atom decreases, right? As you go down the group, it increases, but going from left to right, you will have a decrease. So manganese 3+ is smaller compared to titanium 3+. For that reason, you would expect manganese complex between the titanium and manganese complexes, the manganese complex to be inert, and relative to this should be labile. This has nothing to do with the ligands here. All ligands are same, the charges are same. Here, the size is the one that determines whether or not a complex is inert or labile. Okay, that is rule number 1. Let's look at rule number 2. Rule number 2 tells us complexes with electrons in the high-lying orbitals are labile. What does this tell me? So for example, if I have manganese 4+, when you look at the crystal field splitting, right? So in manganese 4+, it's a 3d3. You have electrons in the low-lying orbitals, but you have none in the high-lying orbitals. When you don't have electrons, if you have electrons, it becomes labile. If you have no electrons, this becomes inert. Let me give you another example. Let's say if I have Mn NH36, which is a strong field ligand, I'm sorry, with a 3+. Again, we see, we'll just keep the same, not ammonia, strike that out, we put water because we want to compare both of them. So when you do that, this is the configuration I have. I have now an electron in the high-lying d orbital. This will make it very labile. This is a very important rule. Now, some of you may be wondering, why is that the case? We're not here to memorize these rules. We are trying to understand why this is the case. Any thoughts on this? Why would having electrons in the high-lying orbital make the complex not stable?
Wasn't it because the lower the T2G was considered stable and the top was considered unstable?
No, we did not say that stable. Stability is, no, we're talking about the lability of the complexes. To understand this, we need to go back to your octahedral geometry, right? That's your octahedra. Now, these are the directions for the EG orbitals. That's your x squared minus y squared, and that's your z squared. When you don't have electrons in x squared minus y squared or z squared, which is the case here, there is no repulsion between the metal and the ligands. The ligands get strongly attracted. On the other hand, if you start having an electron in either x squared minus y squared or z squared, then you're going to have a repulsion between that electron and that ligand there. That repulsion weakens the metal ligand bond, and hence it makes it more labile. That is the reason why we say complexes with electrons in the high-lying orbitals are labile. This is the detailed reason why that is the case. Am I making sense here?
Could you repeat that again?
Okay, when you have electrons in the EG level, the EG is derived from two orbitals, dx squared minus y squared and dz squared, right? Now, these two orbitals are exactly in the line of the metal ligand bonds. When you don't have any electrons in x squared minus y squared or z squared, the metal ligand bond is very strong because there are no electrons in between the bond to repel the electrons of the ligand. Am I making sense to you? On the other hand, if you have an electron in the high-lying orbitals, those electrons, if I have more electrons, in fact, more repulsion they have, so these ligands are not held very tight by the metal because of this intervening electrons in the x squared minus y squared and z squared, and makes them very susceptible for ligand replacement. In other words, they become very labile. Okay? Paula, does that make sense to you? All right, so let's go through a couple of more rules, and then we will take some examples to predict the lability and stability and the implications of it too. Number 3. Complexes with empty low-lying d orbitals or what do you expect? Or
And they're labile.
I'll give you the reason again why that is the case. Let's look at some complex, something like Pi 4+ complex. Titanium 4+ is a D0, which means there are no electrons in either T2G or EG. These are all empty. There are no electrons here. Okay. So here is the way we approach this situation. Let's imagine that I have an octahedral complex in a cube. So I have ligands on the centers of the faces. That's the original complex. And these are all the XYZ directions. The ML-ML bond is your x-axis, that's your y-axis, and this is your z-axis. Right? Now, if you were to locate the dxy, dyz, and dzx, where are they now? They are not along x, y, and z axis, right? They are between the x and y axis, y and z axis, and z and x axis. So this is in between. So when you don't have electrons in these orbitals, that means whenever a new ligand comes, the L prime, usually what happens is the new ligand always tries to insert itself between the original ligands. And if there are no electrons in the x, y, y, z, z, x, that tells you that there will be no repulsion to kick this incoming ligand away. So it becomes attracted to the metal because it doesn't see any electrons, there is no repulsion. So the new ligands are free to go and attack the metal. So the old ligands will leave then. So that is the reason why they are very labile. Okay. That is the rule number 3. So let's now look at the last rule. Rule number 4, complexes with filled T2G and empty EG, or what do you think your guess would be? There are no electrons in the EG high levels, and the T2G is completely full.
Inert.
You are absolutely correct. Whoever answered, I didn't see. Is it Medina?
Me. Yeah.
You're paying attention to this. You're absolutely correct. That is inert. No exceptions. Again, for the reason I told you, right? If you have no electrons in EG, that means the original ligands are held very tightly. Because you have electrons in the low-lying orbitals, the new incoming ligands have to fight these electrons because there's going to be repulsion between these electrons and the electrons of the new incoming ligand. That repulsion kicks them away from the complex, keeping the original complex extremely stable. In other words, it's going to be inert.
Is it that it's also explained by VBT?
Hmm?
Is it also explained by VBT, valence bond theory?
Valence bond theory,
Since the metal and ligand has a strong bond.
exactly.
We
The
can say-
bonding is still the case. Yes, valence bond theory, yes. But
Alright.
the caveat here is, instead of looking at the D2sp3 orbitals, which are all homogeneous, we are looking at the splitting of the d orbitals on the metal and looking at that electronic configuration as a means of predicting the lability or stability of a complex. That answer your question, Sahil?
Yeah, I remember if there's an inner orbital complex, so I usually say if it's inert. If there's an outer orbital complex, I can say it's weak and labile.
Those are different things you're talking about. The inner orbitals, outer orbitals are very different. Here we're talking just about the metal itself.
Okay.
We're not looking at the influence beyond the outer sphere of the complex. There are two, what you're talking about, of course, they do exist, the inner sphere mechanism and the outer sphere mechanisms. But this is more like looking at the metal itself. Okay,
Got it.
great, excellent. So let's look at some complexes, see if we can predict whether they're labile or inert. Remember some time ago we said there are two complexes of iron cyanide. One is deadly, one is not. Okay, so let's look at those complexes. See, one is FeCN6 4 minus, the other one is FeCN6 3 minus. Okay, if a complex is inert, that means it cannot exchange its ligands. Here the ligands are cyanides. Cyanides are extreme. As you know, they're very toxic. They can kill people in a matter of minutes. So if a complex is labile, then it releases the cyanide into the human body and kills them. On the other hand, if a complex is inert, it will not be able to release the cyanide, so it is considered to be safe. Our job is to argue, based on the rules that I have told you, which one is inert and which one is labile. Of course, our game starts with looking at the electronic configurations. In one situation, iron is in 2+, other one is iron is 3+. Iron 2+ is argon 3d6, and iron 3+ is argon 3d5. Is cyanide a strong field ligand or a weak field ligand? What did we learn in the previous class? Remember I gave you a spectrochemical series?
It was strong, right?
You're absolutely correct, sir. Please. If you're not following the previous lecture, if you look at, try to understand this, it becomes a little complex, but we talked about this already. So in the case of iron 2+ and iron 3+, we look at the d orbital splittings. So what happens in iron 2+? The crystal field stabilization energy is very large because it's cyanide, strong field ligand. Iron 2+ has 6 electrons. So all 6 electrons have to go into the T2G. No electrons in the EG. If you look at iron 3+, you have only 5. Again, it's a strong field ligand. So it's going to be 1 unpaired electron here. Right? So from the rule number 4, which one will be inert? What did we say the rule is?
If the T2G is full, then it's inert.
Say that again slowly, sir.
You said if the T2G is filled and the EG is empty, the chemical or the ligand is inert.
The complex is supposed to be inert, right? That's
Yes.
exactly what it is. This is inert. Because it has empty EG and filled T2G. Compare that here. Is your T2G completely filled? There is always a hole here, right? There is an empty space here, which iron 2+ does not have. And that fact that T2G is only partially full, not completely filled, makes it Laval. So which one is dangerous? Which complex is dangerous? Hexacyanoferrate 2 or hexacyanoferrate 3?
3.
Hmm?
The third one, the 3 one.
This one?
Yes.
This one is what? Dangerous or not so dangerous?
It's dangerous because it would release the cyanide and it would kill people.
That's exactly what happens. See the medicinal chemistry. So what do doctors do then if somebody is suspected of cyanide poisoning?
Give them something that will bond with the cyanide.
And then don't release the cyanide back, right? You want something like a sponge that selectively sucks up all the cyanide in the human blood, but don't release any cyanide back to the bloodstream. So what can we do then? If somebody is suspected of cyanide poisoning, the doctors will do what they call ferrous ammonium sulfate solution. Ferrous ammonium sulfate is FeSO4 NH4 twice SO4. This is a water-soluble iron 2 salt So if somebody is suspected of cyanide poisoning, giving this solution to the patient, this iron 2 will suck all the cyanide and make this complex, hexacyanoferrate 2 complex, and this complex is inert, so it saves the life. So for those of you who may not be familiar, all scientists working with a cyanide are supposed to keep at least a 1 liter solution of ferrous ammonium sulfate next to that. If there is an accidental ingestion of the cyanide, the recommended thing is even before you go to the doctor, you must be able to drink that. It's not pleasant, but it's definitely better than the alternative. So now you understand the importance of the medicinal chemistry of complexes. On the other hand, if you were to use iron 3 salts, that would not do any good to you. Because iron 3 plus, of course, it also complexes, but then that complex is so labile, it releases the cyanide back to the bloodstream. So it's good to know the reasons, the electronic factors, and why some complexes are labile, stable, and their applications and implications of the lability. In fact, when we deal with the catalysis of these complexes, all this lability and stability makes a very important aspect. Why some complexes are active, some are not active catalytically. So how do you design a catalyst? Right? So definitely something like this will never be a catalyst because this is so inert. It will not exchange the ligands. It will just hold on to all the ligands so tightly. Am I making sense here, folks? Are we okay so far? Okay, the next thing is formation constants. Graph of complexes. So of course, whatever I'm going to present now can be applied to tetrahedral complexes too, but we'll start with the octahedral complex. So if I have a metal and 6 ligands, we get Ml6 complex, right? A metal ion and 6 ligands. The question here is this a concerted step? Is it a single step, or does it occur consecutively? So for example, the M will bind with the first ligand to make Ml with a constant of K1, that's the first equilibrium constant. And the Ml then adds on to the L to give Ml2, the formation constant of 2. Finally, you have Ml5 plus L giving Ml6 with a formation constant of 6. So if you were to add all the reactions, if you add them up, that's what you get. Because Ml cancels, Ml2 cancels out, and whatever results is basically M plus 6L giving Ml6. So this one, Kf, basically is the product of K1, K2, K3, K4, K5, and K6, of course. Because this overall reaction is the sum of all the individual reactions, so the equilibrium constant must be the product of the individual equilibrium constants. In general, what happens is the equilibrium constant 1 is greater than 2, greater than 3, and all the way greater than 6. So the smallest equilibrium constant is for the K6, and the highest equilibrium constant is K1. Why is that the case? simple physical chemistry of collisions, right? So when you're making an octahedral complex of a metal, when you have the first ligand, you occupy the space here. So when the next ligand comes, if that tries to replace this, it won't happen. It has to find another spot. So the efficiency of the collision should be good. And if you go to the third ligand, now any collision between these two ligands and the third will not result in the product. So the possibility of the collisions decreases as you increase the substitution. So highly substituted complexes like ML5 will have very few successful collisions that will lead to the formation of the complex ML6. Okay, so that is generally the trend. But then in some cases, what happens is K1 greater than K2 greater than K3, suddenly K3 is less than K4 and greater than K5. So there is a reversal of the order here. It does not happen too often, but it happens enough number of times that we need to get concerned about this. Okay? We give you an example of why there is sometimes a reversal in the formation constants. Okay? Let's say we have a replacement of cobalt H2O6 3 plus with cyanide, 6 cyanides to make COCN6 3 minus plus 6 H2O. In here, something crazy happens here. The early indication that something may not be right here is when you're trying to exchange a weak field ligand, such as water, with a strong field ligand, such as cyanide. Okay, so in here, the reason for that is, if you look at the electronic configuration of COH2O6 3 plus, cobalt is 3 plus here. Cobalt 3 plus is a argon 3d6. In a weak field ligand, this is the configuration of the cobalt molecule, but on the other side, we have so clearly from the rules we talked about, this complex is very labile because it has electrons on the in the high-lying d orbitals, right? Whenever you have this complex is supposed to be labile, but on the other hand, this one is an inert complex. So as you progressively replace the cyanide with the water there, at some point what happens is suddenly the complex becomes inert. So it becomes very stable. And that is where you will see a reversal in the equilibrium constants. But if you are replacing a weak field ligand with another weak field ligand, and if the complex is not going to be inert, in those cases, you will still see the usual form. But whenever you see an exception to the general rule, that is when you have to think about the possibility of having a change in the crystal field stabilization energies. Am I making sense here, folks? Any question? Okay, let's look at another important aspect of coordination complexes, what is called chelate effect. So far, all the examples that I have considered here are monodentate ligands. Only one atom of the ligand attaches to the metal. Sometimes you must have seen from the previous lectures, you may have a ligand that could be bidentate. In other words, two atoms in the same ligand can bind simultaneously to the metal, or sometimes it could be three of them, right? So whenever you have a bidentate or a tridentate ligands, there you have a possibility of getting very high equilibrium constants. Let me give you an example of that. Let's say if I have iron, H2O6, let's say 2 plus we have 3 molecules of ethylene diamine. Ethylene diamine is a bidentate ligand. So all of you know it is NH2, CH2, CH2, NH2. That is what ethylene diamine is. So there are 2 nitrogens that will claw and hold on to the metal. All right. So when you make this complex, FeN3, 2 plus 6 water molecules. So gas. Yes. These reactions are extremely favored. Multidentate complexes, bidentate, tridentate, tetradentate ligands form stable complexes. Again, the reason for this is by entropy itself. If you look at the total number of particles on the left-hand side, I have 1 complex particle and 3 ligand particles, 4 particles. On the right-hand side, I have 1 complex and 6 water molecules, 7. So you're increasing the number of particles from 4 to 7. And physical chemistry tells us that if you increase the number of particles, you increase the entropy. And second law of thermodynamics says that those reactions should be very favored. So anytime you have ligands that can chelate, that is multidentate ligands, form stable complexes because they're all entropy favored or driven by the increases in the entropy. So the driving force for the formation of multidentate ligands is an increase in the entropy. Always, every time you try to replace a monodentate ligand with a polydentate ligand, you have a complex that is very stable. Am I making sense? So finally, we'll talk a little bit about what we call steric effects. We have chelate effect, we have steric effect. Whenever you have bulky ligands, ligands that are pretty large in their average molecular dimensions, those complexes are generally not very stable because of the steric effects. So if you are trying to place the ligands in an octahedral field, as long as they are simple, there is no repulsion between the ligands. But on the other hand, if you have a ligand that is a very large organic molecule, so the steric repulsions destabilize this complex. So complexes that have very large ligands tend to be a little bit unstable because of the steric interactions. All right. So based on the stability of these complexes, we have what we call Irving-Williams plot. So here what you do is you look at the relative stabilities of complexes as a function of their position in the periodic table, what you find is when you plot several complexes, you always go like this, and then there's a drop. So for example, if I have barium, strontium, calcium, magnesium, these complexes are generally low formation constants. Barium has a extremely small formation constant. Why is that the reason? What can we attribute to the smaller Kf value for barium complexes? If you go back to rule number 1 about lability and stability, what did we say? If I have a complex with a very large metal ion like barium, is it supposed to be stable or is it supposed to be labile?
Inert.
You're correct. That's the reason why the formation constant is very small here, because the ligand interactions with a larger metal is very weak, so the formation constant is weak. If you go to strontium, it's slightly smaller, so it's a little bigger. If you go to magnesium, it's awful smaller, so it's more stable. And finally, you have on the top copper, copper 2+ of all the complexes makes the stable things. The reason for that is the Jahn-Teller distortion. Remember, we talked about this, that the Jahn-Teller distortion stabilizes the copper 2+ complexes, and hence copper complexes are generally given highest formation constant. So for any given set of ligands, one can draw the Irving-Williams plots, IW plots, for a variety of complexes. I'm just showing you how to read them, how to understand, and how to rationalize the graphs here. Okay? Basically, it kind of summarizes all that we have been talking about. Okay? Questions up to this point? Anything that's not clear? Covered quite a lot of ground here quickly. Talked about the Jahn-Teller distortions. We talked about the lability versus inertness concept. Gave you lots of examples. Then we kind of gave you the rules for predicting the inertness of the lability of a complex, 4 important golden rules. And then we talked about the formation constants, the successive formation constants, and the trends in the successive formation constants. You know, what is the general trend and when do you see anomalies? We also talked about steric effects, Fields effects, and then we talked about Irving-Williams plots. So that kind of gives you an idea about how coordination complexes are discussed in the advanced inorganic chemistry course. That's all I would like to try. Of course, you can get on to other things, but we just don't have the time. When you open up another can of worms, like the molecular orbital description, we talked about crystal field theory, right? While crystal field theory is successful in most of the cases, it has its own shortcomings. So we have something called ligand field theory, that is purely molecular orbital approach with symmetries and looking at. Remember, we talked about symmetry adapted linear combination of atomic orbitals. So we can also look at the ligand symmetries and the metal symmetries and come up with the molecular orbital description too. We're not going to go get into that because we have other topics to cover too. But I hope you had some good idea about complexes. Any questions so far, folks? So for those of you who are wondering what the exam will cover, you will not see anything that is not discussed in this classroom in all 3 topics. One is the molecular orbital theory of polyatomic molecules, which we covered in the beginning. We talked about symmetry adaptive linear combination of atomic orbitals. And then we covered quite a lot on the solid state chemistry, crystal structures, the densities, the packing fractions, the lattice energies and all that stuff, ionic compounds. And the coordination complexes, we talked about the bonding and coordination complexes, crystal field theories, and then magnetic moment of coordination complexes, and finally about the lability and stability of the complexes. So that's what the exam will be, basically. It's quite a lot of ground that we have covered. Any questions?
Yeah, quick question.
Yes.
Is the test going to be like how tests were last semester where everything was multiple choice?
Right, yeah. In fact, you'll have a sample exam, right? Sample test. I don't think you had sample test last semester in inorganic chemistry.
We did not.
So now we have a practice exam.
Okay,
What kind
thank
of-
you.
Yeah, that gives you an idea about how questions are asked. For the practice questions, some of you have said that you also want to practice doing questions in time. Oftentimes that's always useful because if you're going for GREs or standardized testings, you are given a finite amount of time in which you have to answer the questions. So sometimes speed is also very important. So I put about 2 hours time, although I'm sure most of you will be able to finish it in 40 minutes. Okay. All right, if there are no other questions, I want you to go back and again read the topics. Now you know all the titles, descriptions, examples. And I wish you well with the sample exam. And then we will see you next Thursday around the same time. We'll meet very briefly to see if you have any questions still, like maybe you did the sample exam and then somehow you think that maybe I didn't understand this well. So can we go over that one more time? So that's the thing. Because in the actual exam, that's different exam. So you just want to make sure that you're prepared with all the topics. All right, so if there are no questions, we will meet you in person next Thursday. And I wish you good luck with your sample exam or the practice exam next Tuesday. All right. See you all then.
Thank you for